All right, so my name is Henrik. I'm here from Sintef. I'm going to talk about time-sensitive networking today, in particular about using it for proof of concepting. A very rough sort of outline for what we're going to talk about. A quick introduction. Then I'm going to quickly dive into time-sensitive networking, all the standards and everything. I'll be brief, so I won't bore you to death. Then I'll cover NetChan, a small library to use TSN with a distributed controller example and some conclusions at the end. For those interested, you can grab the slides. So, before we get going, let's set the stage a bit. I'd like you to meet Bob. He's a newly graduated engineer hired at Men at Arms, which is a small family-run company that builds swords. He's an eager engineer trained in robotics and control theory, and his place in this new in this business is a production optimizing engineer. Basically, he's going to take the company into Industry 4.0, which is all the hype. And he is very optimistic, and he likes to make things automated and complicated. And we'll see how that goes. So our factory, it's a fairly simple setup. You have some smithies that make swords that you sell for profit. And of course, what the factory really wants is to make more money. Enter Bob. So Bob starts to think, how can we optimize and make this more efficient? And the obvious solution, of course, is to automate the stacking and the warehousing. So you can add some more smithies, you can make sure that everything runs smoothly and efficiently, and as a result, you should get a lot of money. Sounds familiar? Of course, it doesn't work like that, because things aren't exactly as deterministic as Bob thinks. The robots will move a little bit, so the stacking fails, the automated warehouse does not work as advertised. So he has to revisit the whole thing, and he needs to add some sensors and some controllers and some feedback loops and everything. And then once the arm is capable of finding the robot and stacking everything, then things run smoothly, which is great. Of course, then management notices this and thinks we should increase production because then we can make even more money. And of course, to handle this extra load, you add more robotic arms, you add more robots to do the stacking, and you add a bunch more smithies to make swords. And anyone can guess how this will go. It will, of course, go badly, because now you have a much more complicated and complex setup with a lot more state you need to take care of. So Bob does what Bob does. He adds more sensors, he adds controls, he adds object trackers, he adds orchestrators and waypoint planners, more sensors, and now everything should work. And to sort of stitch all of this together, you need to share a little bit of state between the components, probably forward some emergency signals. Maybe you want to have camera and LiDAR shared between the systems. This sort of grows a bit out of hand. And you end up with like an unholy mess of cables and state and everything you need to share. And sort of the inherent problem in what Bob is facing here is that when you build distributed or real-time systems, you typically connect sensors to a single system. There's a one-to-one connection. You may have a distributed system, and you may have multiple systems sharing the same network, but all the sensors and control flow between the nodes are typically one-to-one. Ideally, what you would want is to just use the network as a backbone to share all of this. So if you can attach your sensors and everything directly to the network, not only can you share information more efficiently, but you can also share sensors to more than one system. So the LiDAR here, for instance, can be shared by 2 different systems and several nodes in both systems. So if you can do that, you can sort of deduplicate sensors a bit. So what we're going to do sort of as a baseline here is to use the network as the backbone. This removes the one-to-one cabling between the sensor and the system. You still need a cable between the sensor and the network, but you don't have this cables going everywhere else. You can also move the analog to digital converter closer to the actual source. If anyone has worked with analog devices, the 420 milliamp current issues is a lot of fun. I encourage you to do so if you haven't, and then realize why networking is more fun. And finally, networks are scalable. The bandwidth in a network is massive, and you can generally connect more things to your device through the network than you have physical connectors on the back of your device. There's a finite place of things you can connect to your system. With a network, you can greatly expand this. I have to be honest, the network is not going to solve all of Bob's problems, and there will generate a few new ones, and we'll try to tackle some of those now. Did I? No, I didn't. Okay. One of the things we need to look at is what is called deterministic networks. So what is determinism when it comes to a network? And sort of a key word here is composability. We need composability in our real-time systems, and by composability we mean that you need an attribute that does not affect other attributes. So in real-time systems, we typically talk about CPU scheduling. So my execution time on my critical task should not be affected by some of the other tasks in the system. We want the scheduling to be composable. The same goes for the network. So my critical traffic should not be affected in any way by someone looking at YouTube videos or someone uploading a new CNC G-code file to the machines. Nothing else in the network should affect my critical traffic. And my critical traffic should not affect other critical traffic streams. And it's also important to note that a network will drop your traffic. It is under no obligation to protect your traffic unless you explicitly instruct it to. So in sort of a transient overload, when the network has too much to do, it will just start dropping packets until the load situation is manageable. That includes your critical traffic. And even though you have, at the face of it, low utilization, you will have transients where suddenly the buffers run full and it will just randomly drop packets. And that can be frustrating to try to track down. As with CPUs in real-time system, it's tempting to think I can just add more resources. I can get a network with higher bandwidth. Yes, but there will still always be situations where you will have short transient windows that you will exhaust your buffers in anyway. So what we need is quality of service mechanisms. There are several excellent mechanisms. We're going to talk about TSN today. There are many others. There's a link to a paper at the end of the slide to a broader overview. But by and large, a network is basically just a sequence of buffers that will add delay to your traffic, and these buffers can run full, and we need to manage those buffers. So that's sort of the core of what the TSN standards attempt to do. So this brings us to TSN, which is a set of open standards. As I said, there are several ways to manage the networks. There are some closed standards. There are some closed and proprietary solutions. And these IEEE standards, they are open and can be freely supported by several vendors. It handles a broad set of use cases. It started out using audio as an example, and it's moved into automotive, aerospace, 5G networks, and industrial networks. The nice thing with TSN is that it follows the Ethernet standard. So that means that as the Ethernet speeds increases to 40 gigabits and 100 and 400, TSN will follow. So we can have quite massive, at least compared to traditional retail networks, we have really, really massive bandwidth available to play with. TSN will give you what they call a bounded end-to-end latency, meaning that there will be some latency and there will be some jitter, but there will be an upper bound on how delayed your traffic will be. It also sort of from the standard gives you excellent clock synchronization, so you will have PTP, and if all the equipment supports TSN, you will have guaranteed 1 microsecond clock accuracy. It will often be orders of magnitude better, but it will at least be a microsecond. And there are some extra steps you can do, replication and more tricks to safeguard your traffic. One caveat, the entire network, all the bridges must support TSN. If you have a switch or a bridge, as they call it, that do not support TSN, that's where the TSN boundary is. That's where your network stops, basically. So over the years, they have created a few standards and amendments, typically grouped into 4 categories with sort of the profiles tacked onto the end there. You have a set of time synchronization standards that gives you PTP. You have some flow management. That's how you communicate with the network to reserve resources for your streams. Then you have some integrity and robustness. Typically, you have frame preemption, frame replication, etc. For this talk, traffic control is the most relevant one. That's where you have the shapers. The shaper are the part that orchestrate how the traffic leaves your system into the network to make sure that it flows as predicted. You also have the stream policing there, which manages incoming flows in case you have some misbehaving stations. And finally, you have the profiles. Now, the profiles are not standards per se. They are more a grouping of which amendments and standards are relevant for that use case. So you have the AVB standard that gives you sort of the basic credit-based shaper, PTP, and stream reservation protocol. Then you have fronthaul, that's for 5G. And the rest one are sort of grayed out because they haven't been fully standardized yet. They're working on those, where you have aerospace, automotive, and interestingly, at the end, you have TSN for industrial automation, which sort of tries to bring TSN into the factory floor. So that would have been helpful to Bob in our case. They started working on what was then called AVB back in 2008. They formed the task group in 2006. And you sort of have the first grouping here. This is the AVB work. And then they realized that we can do a lot more than just audio and video with this. So they renamed to time-sensitive networking. And then they started to work on a lot of more standards for several more shapers, several more ways to mitigate problems, improve bandwidth utilization, etc. And for our case, we are most interested in sort of protecting the streams in a small network, and you also see stream classes and shapers. The initial one from the credit-based shaper uses stream class A and B, and those gives you a 2 millisecond end-to-end latency, and was primarily used for wired networks. And they also had class B, which gave you 50 millisecond, and the idea was that you can have a wireless link thrown in as well, and then you need some more buffers and safeguards. You also have what is called scheduled traffic. That's the time-aware shaper. That gives you a 100 microsecond end-to-end latency in a gigabit network over 5 jumps, I think. So that's a really, really short time, and that's about the time you need to actually transmit 1,500 bytes over a gigabit link, then queue it and forward it on a switch for a couple of microseconds, and then forwarding it on a next link. If you want to do that for 5 jumps, that totals up to 80 microseconds or something. So you can't do much better in a standard packet switch network with store and forward. You can bring it down if you want to play with cut-through switching and all that. Then you're into a whole different domain than what we're looking at here. Then you need to sort of specifically engineer your network on a whole new level. There's also a few other shapers, the cyclic queuing and forwarding and asynchronous traffic shaper. That's useful for alarms and slightly longer periods. So just going through some of the shapers really, really quickly. The credit-based shaper is called a class-based scheduler. meaning that all streams in your network will be lumped together in that class. That makes it really scalable. It makes it really low overhead for the network hardware. But there are some few issues you need to be aware of. It won't do frame ordering, for instance. So if things come out of order, the shaper can't help you. Its only configuration parameter is what they call the idle slope. That's basically your bandwidth. And all this traffic is averaged over what they call an observation interval. But that interval is sort of a mix of the bandwidth you have and the frame size. And that sort of brings the interesting take on the credit-based shaper, because we always talk about the bandwidth requirements that you have, and that does not exist in CBS. What you do there is you reserve your frame size. So you don't reserve 3 megabits for your link, you reserve 750 octets or bytes for your traffic. And then the shaper assumes that you will send at 4 or 8 kilohertz, so rather often, and gives you a bandwidth as a function of that. So that's sort of you have to think about it in an odd way. Then you come to the time-aware shaper. This is the really, really low latency one. And what you do there is you sort of reserve a set of slots through the network, saying, I'm going to send my traffic in this slot. And then all the switches in the network will be ready at that time. And it will stop anything else from being transmitted. So when you're ready to transmit, the network along your path is not sending anything else. It's blocking everything else from sending. And then you can just shoot straight through. And that is how you get these really low latencies. And it does this by using what they call a gate control list that it has to distribute to all the bridges. The problem, of course, is that this is really, really sensitive to clock accuracy. So if one of the bridges, so I have 4 bridges called bridged 1 in this slide. So please just rename them to 1, 2, 3, 4 when we talk about this. So, sorry. So if one of them is out of sync, it will stop the traffic. And when it eventually then catches up and sends, the schedule has moved on the next switch, which means that it will block until the next unrelated slot arrives. And then it will be forwarded. So this gives it, first of all, it gives it a really long delay that it shouldn't see. But perhaps worse is that second slot may not be its slot. It could be for another stream. So not only will it be delayed for a while, but it will also interfere with some other unrelated stream that had targeted that slot. So that's one of the problems with the time-aware shaper, is that it's really sensitive to these invariances in clock accuracy. You also need to engineer your network to orchestrate this. And finding sort of the total gate control list for the network is NP-hard. That's a knapsack problem. So if you have a big network, that is going to take a while. And that also means that if you want to add a new stream into the network, you need to recompute the whole thing. So there's not much dynamics in this setup. Very briefly about ATS. It has been standardized, but it's not implemented on any switches that I know of. It would be nice, though, because this one handles a lot of the problems we see with the credit-based shaper. It allows you to send sporadic messages. It allows you to use periodic streams with a different period. And it can also do reordering between streams in the same class. But it's a bit more complex than the other ones. And is also not susceptible to timing problems like the time-aware shaper. And finally, I'm almost done with this now, so just CQF, that's just a peristaltic shaper. It's just easier to analyze and see how long the delay through the network is going to be. So it's much simpler. You can use different periods. It works with periodic traffic, and that's it. But yeah. So how am I for time? Yeah, that brings us to NetChan. So NetChan is a small library that we've written to try to experiment and play with TSN to see can we actually use this for something useful. because we have a lot of standards and a lot of theoretical talks that TSN is great. But as you saw, there's a lot of standards and amendments and protocols and daemons and whatnot, and we try to sort of bake some of that at least into this library. And we use a fairly simple abstraction in NetChan, what we call logical channels. So basically, we give you a pipe, and what you put into the pipe will pop up on the other side, hopefully within the bounds of the network. It hides a lot of complexity. It does stream reservation for you. It assumes that you run PTP daemon to synchronize the clocks. It's written in C for a couple of reasons. First of all, I know C, so that was easy. But also because C is excellent for system libraries. We want to link this to other languages, so C++, Python, whatever, and that's very easy to do from C. So this is meant as a system library, not as a standalone application. So I know there's Rust out there, but it was very consciously picked C for this. It runs only on Linux. We need to use some of the tools we have available in Linux, especially QDisks and sockets. It's freely available. It's on GitHub. There's some assembly required. There is a couple of bonus slides at the end we can have a look at later just to see the setup, what you need to do on the system to get this up and running. There's some awful QDisk commands. What you get. If you want to communicate between two hosts, let's say A and B or two processes, the channel between them over the network is what NetChan gives you. And we sort of describe this using what is called a manifest, which is basically just the address of the channel, the period, and the size of the data you want to send. And in a system, you can define multiple channels that will have multiple endpoints, either on one host, or you can split to several hosts. TSN is great because it uses multicast, so you can send this to multiple hosts if you want to. So you can send one to many. You can't receive from many to the same channel, but you can sort of duplicate the traffic out, and the network will do that for you. In order to get this up and running, as I said, you need Linux, preferably running preempt RT. That's just to make your system more predictable. There's a couple of network cards that supports what we need. In particular, Intel's i210 and 225. They have the credit-based shaper on the network, so you can sort of pump out the packets in sort of the sequence you need without doing that in software. They also have what is called launch time, so it means that you can schedule when a frame is going to be sent. You need QDisks. In particular, you need the MQ-PRIO, so you can take a socket priority and map it to a hardware queue. And you need the QDisk for CBS and earliest transmission first. This is all available in Linux since 2018, I think, so it should be fairly easy to obtain. Your network needs to be TSN capable. Biamp has a nice list of supported switches. You need a standalone SRP daemon because you need to communicate with the network. And then we have a plugin in NetChan that communicates with that daemon. PTP needs to be running. And yeah, there's the appendix at the end. Read the docs for TSN is a really good summary of how to actually set up your system. So if you're looking into this, that's a really good place to start if you want to set up your own Linux end station. So we tested this for a while. So this is sort of the nice rack I have in my office. In the top here, I have two Catalyst switches. They are not the quietest of switches. So I have noise-canceling earphones, but they sort of slowly drives you mad. I have two test machines at the bottom that have i210 network cards attached, two of them. And I have two other workstations that I use to generate noise in the network. And on top here is sort of an unrelated, that's a 5G base station that we also have hooked into this so we can have a wireless link as well. We're not going to cover that today. We're going to use the bottom half here. Before we get into sort of evaluating how things work, we sort of made a baseline of the test system. First, we did the PTP synchronization. So this was a 8 hours and 50 minutes test run where I did everything I could on the test machines, running multiple parallel makes, swamping it with unrelated network traffic, etc., to see how the network clock was actually synchronized to the network. And it worked really well. The network card was synchronized to within 11 nanoseconds on the blue one. The listener, that was the furthest distance away from the groundmaster, so that had slightly higher inaccuracies. But by and large, the clocks were really tightly synchronized. We also ran cyclic test on the machines. So this is just both machines lumped together, just to measure how accurate and how well the Linux kernel performed, basically. And we managed to sort of squeeze it down so the wake-up accuracy of both systems were within 16 microseconds. So what cyclic test does, it just periodically puts a thread to sleep and then wakes it up, and then it have a look how close to the target wake-up time did the machine actually wake up. And the better your real-time performance of your kernel and your system, the more accurate it will be. So this is as well as we were able to get this system running. Without the preempt RT kernel, the maximum was 3 or 4 milliseconds. So the preempt RT really helped us. So our first goal in evaluating NetChan was to see, okay, I want to make sure that my critical traffic between the talker and the listener are shielded from interfering traffic. So we set up sort of this simple butterfly schema where we have a shared link between the two switches. So all the traffic will go across this shared link. And we have two machines that just hammers the network with unrelated traffic. The large packets that we can send and as much as possible. And then we send the critical traffic through and we see how long it takes to get through. And hopefully, even though we do bad things to the network, all the frames should arrive and they shouldn't be more than 2 milliseconds late. So to sort of measure this in stages, we used what is called a write wait and read wait primitive. Since we are sending this as class A traffic, we know that the network gives us a 2 millisecond end-to-end guarantee. That means that when I send a frame, I know that within 2 milliseconds, the receiver will have received that frame. So if I send a frame and I sleep for 2 milliseconds and I wake up, ideally, it should be possible for the receiver to do exactly the same, the receiver frame, sleep until it has gone 2 milliseconds after I sent it, and then we should wake up at the exact same time. So that's the thing we're testing here. And then we're measuring how close to the target wake up both of them are, and see how it performs. And the code on the right here is just the manifest I talked about, just describing the channel. So you say, okay, I'm using stream class A. I'm sending basically a sequence number just to detect if I lose frames, and some multicast address that I want to send it to. And you have a unique stream ID for that particular channel. So looking at the talker, to use NetChan, you create a net handler and a transmit channel. You just have to wait for SRP to stabilize. Basically, you have to wait for the reader to also attach, so you don't start to send before everybody's ready. This one, that's just a helper to sort of make you have a periodic, so you don't swamp the system. There are some caveats in NetChan when you use the CBS, so we have an extra helper for pacing out the traffic. And then we just send and wait. There's a send and there's a send wait. The send will just send immediately and return. The send wait will look at the class you're sending. So if you're sending with class A, it will wait for 2 milliseconds. If you send with class B, it will wait for 50 milliseconds. So just a helper to help you to achieve that. And then it just cycles forever. Likewise, the receiver, you create a handler, you create the receive pipe, and you wait for the talker to arrive, and then you wait. And then read wait will look at the timestamp for when the sender sent the traffic, compute so it finds 2 millisecond offset, and then it will wake up. And all within NetChan, it also grabs some timestamps, so we can analyze the logs afterwards. So that's what we did. The red line is just added noise to the network. Our first attempt when we did this with and without TSN. So the first attempt was just to swamp the network with noise, and that gives us 0 data for the unprotected traffic because nothing got through. So we added the pulse so we could send data and actually see that, oh, when there's no noise, things actually get through. And as a nice effect, you also see that, yes, your traffic will be affected a little bit by noise. The delay goes up, end-to-end delay goes up a little bit, but the largest outlier we have is 180 microseconds. And I think most of these outliers are within the Linux kernel. We didn't have all the timestamping when I captured this data set, so I'm not fully sure. But we did not lose anything, so TSN was capable of protecting all our traffic, and everything arrived within, well within 2 milliseconds. And then, of course, we can look at simultaneous wake up. So when both systems are ready to wake up, we can capture the local timestamp and see how close together they wake up. And the relative difference between them was roughly a quarter of a microsecond on average. The largest outlier was 15 microseconds. Negative means it woke up late. It's just sort of the way you do the subtraction here. So it's the same accuracy that we got from cyclic test. So that means that it worked as well as we could on the systems that we had. Since then, we added some more timestamping that we can apply to the system. So when you send things through NetChan now, it will add timestamps as a frame goes through the system that you can extract later on and analyze if you want to. In particular, it will capture a timestamp when you hand over a frame to the pipe, and it will also take a timestamp when NetChan actually takes that frame and sends it. For the credit-based shaper, those are the same. If you want to use the time-aware shaper, so schedule when you send it, this will differ. And then, of course, we also get report from the network card itself when it actually sent the frame. You can extract that from the network card, so you can have account for latencies over the PCI Express bus, etc. And on the other side, on the receive side, you have the receive timestamp when it arrived at the network card itself, and finally when it was handed over to the application at the other side. Sorry. Okay. And from this, you can sort of make nice graphs to have a look. The red one is the total end-to-end latency, and you can break it down into delays from handing it over to the system. By God. Etc. So you can track down where your latencies are. The green one is the network latency, so when it leaves the network card until it's received. And those timestamps are captured by the network card itself, so they are fairly close to the wire. So building on this, we decided to say, okay, let's see if we can distribute the controller over a robotic arm. So we have a UR10, that's a 10-kilogram cobot, an arm that we can control. And ideally, we wanted to have a small IMU, that's the one on the left there. So that has a 9 degrees of freedom, so it has a gyroscope, an accelerometer, and a magnetometer. And from this, you can find the pose to sort of find out how you oriented it. And the idea was to use this to steer the arm. So I had this vision that I could sort of stand in my office and wave this around, and there would be a robotic arm start mimicking my solution. Of course, it was not that easy because that was a really, really, really bad IMU, so it drifted like crazy. But it was a nice use case for distributing the control. And one of the reasons why it's interesting to look at this is especially for path planning. When you have robotic cells, maybe you need to track an object that moves, like stacking the swords in the earlier example, or you have things hanging from wires, or just people working alongside the robots. You may want the path planner to detect the people and sort of move around them. And that's when you need a dynamic path planner. And those are quite computational intensive to run. And very rarely can you run those on the controller for the robot arm. We also had sort of what is called a UR proxy. And what that is just our way of taking all the state and control signals we send to and from the robotic arm and just mapping it to a TSN stream. So the UR10 controller has what is called a real-time data exchange format, which is a TCP socket. And anyone who has tried to use real-time communication with TCP knows that that's a really, really bad idea because the arm sends at 500 hertz, so you have 2 milliseconds between each frame. And when TCP starts to notice that you miss things, it will retransmit. And that delay will be much more than 2 milliseconds. And by that, the arm has gone through the wall. So you can't really do that. So what we did was just to do a one-to-one connection between the TSN endpoint and the robotic arm, and just map that to a TSN stream and pump that out to the network. We could also extract some other information. Most notably, we used the arm to handle the inverse kinematics of the arm, so we didn't have to compute that ourselves. So we said we want the arm to be here, but we don't want to find all the angles to move the arm there. But the controller can do that quite efficiently. So we just sort of added more, a larger command interface basically through the proxy. So that's what we did at that end, and then we had a very, very simple controller, just a PID controller using the speed of each joint to find the desired position, and we used a path planner to find all the joint angles in order to receive that position, and then we had basically a pre-computed path where we wanted the end effector of the arm to be with an orientation, find all the angles, and we'll just update that over time and feed that to the controller, and then the controller will just move the arm. So that's what we did. Sorry, this is basically the proxy using libURX. Basically, just grab some of the state from the arm and move it out to a TSN using NetChan. So there's no send wait here, it will just send it out. And we will get a new update every 2 milliseconds. And there was a few more pieces to this for all the other states, so incoming control signals and PoC and everything. But this was sort of the gist of it. So it's not much logic going on there. So looking at this whole example, you can split sort of the signal flow down into how often the traffic will flow. So the IMU would give us an update every 10 milliseconds, which would then be forwarded to the poser, basically just taking the IMU signal and computing some sort of DCM to give us where we thought the PoC of the controller were. And then it would send that off to the path planner. And the path planner would have a pre-computed path, and then we could use the PoC of the IMU to sort of steer the arm in addition to this. So as the arm moved, I can use the IMU to sort of gently move it away. This would then, whenever we got a new PoC, we would just request an update through the proxy to the robot to say, okay, this is the PoC I want. What would the angles be? So that would be running at 50 hertz over 2 channels here. And we would also send a new position update to the controller at 10 hertz. And then, of course, you would have the controller running, receiving state updates from the robot every 2 milliseconds. And it would have to reply with a new set of engine speeds every 2 milliseconds. And on the robot not shown here, there was some safety mechanism built in. So in case anything crashes, it will just slowly stop. But from this, you can just describe the channels you need. So the two top ones are state updates from the controller and control signals going back to the controller. And we also have the target pose and joint speed that we need to the controller. Two of these are marked as stream reservation class A, and the other one is marked as time aware shaper, basically just to show that we can target two different hardware queues on the network card. Now, as I alluded to earlier, credit-based shaper is easy to use. It has several drawbacks, but one of them is that it's a class-based scheduler. So in this setting, when I have multiple outgoing streams from an endpoint using CBS, it has no way of making sure that the frames are leaving in the correct order. It will just pace them out as expected. It will not look at any of the paces. So if you have multiple streams that you need to multiplex into a single network card, you have to be a bit careful how you do this. So that's why we started looking at scheduled traffic. This is implemented in Linux using the earliest transmission first queue disk. And you just use the SOTX time socket option, where you can instruct Linux and the socket to say, I want to send this frame at this exact time. And you give it a sort of a buffer time. So within, say, 50 microseconds, I need you to forward this to the network card and schedule it for transmission. And then it will hand it over to the network card. And the Intel cards that we use have this launch time capability that do exactly that. And they have a 32 nanosecond granularity. So as long as the network card is synchronized using PTP, you can give it a PTP timestamp and send it then, and it will do that within 32 nanoseconds. And we could synchronize the clock to 10, 11 nanoseconds, so that was fine. And it will keep all the other frames not yet transmitted into a balanced binary tree, so that even though you enter frames out of order, it will balance it for you. So from this, it was sort of the idea that, okay, we can just implement CBS on top of scheduled traffic. That should be doable, right? So that was a year of pain to do that, because what actually happens, of course, is if you have a lot of traffic going in and everything is moved into a balanced tree. You see where this is going, because then you need to rebalance the tree, and that takes time. And as you start to add more and more streams running at several hundred hertz, the delay can be quite large. And what would happen is you would send a frame, and the network's socket and Linux will say, yes, good, it's in the tree, I will send it when ready. And it will go 50 microseconds, and it will miss the time because it had to reshuffle the tree 11 times by then. And then it will drop the frame and report an error back the next time you send a packet. So you send one, and you send maybe 100 packets, and then suddenly you're being told that, no, I failed to send that one. But of course, it wasn't that one, it was the previous one. And then you had to go back and try to match all the timestamps to find that. So in the end, as you saw in the manifest, you can target both, and it will actually target both hardware queues. So we can use both the credit-based shaper on hardware as well as the scheduled traffic, because if you have multiple streams at 500 hertz, at least on my Xeon machines, you have to use the credit-based shaper for that. It's not scalable to that high frequency of sending. And one of the reason why this fails is you need some buffer in your transmit pipe for forwarding the frames to your network. So even though the network card can send within 32 nanoseconds, you have a PCI Express bus between you and the network card. And the PCI Express bus is not your friend. So in this thing, you see the clock synchronization of the system. And the network card itself was still synchronized to 10, 11 nanoseconds. But that doesn't really help you, right? Because if I want to tell you send this at this timestamp, I need to know what PTP time it is. So I need to synchronize that clock back to the system clock. So move it from the network card to the CPU side. And the PTP daemon and the PHC to sys does an admirable job of doing that. But still, even though the network is synchronized to like a handful of nanoseconds, I still see system clock inaccuracies in my system on the system clock to almost a microsecond because of interference from the PCI Express bus. So if you go in and measure this and sort of count the cycles from reading something from the network card and back, it will be a delay of between 1 to 50 microseconds, depending on what else is happening on the system. And you have no way of affecting that. There are something coming in PCI Express 5, I've told, but I haven't been able to test it. But this sort of makes the clock accuracy a bit of a problem on x86. One of the nice things, though, all of that nonsense aside, is that once you have everything running in a network, it's really easy to debug and attach probes to this without affecting anything. So we've seen that the traffic is composable, that we won't affect the rest of the system by this traffic. That also means that we can hook into that same stream without affecting the rest of the system. It's inherently multicast, so the endpoint will still send a single stream, and then the network will multiplex it for you if you need to. That means that if you want to inspect whatever comes out of the IMU, you can just say, I want to subscribe to that stream, and the network will duplicate it for you, and you can have a look at it. And it's 3 lines of code to hook into it, basically. This allows you to sort of target individual places to look for things. It also allows you to, say, remove the IMU node and replay recorded data if you want to, really easy, because the network is your friend. You can also make more dedicated tools. So this was when we looked at trying to fix the inaccuracies of the IMU. We ended up making this GUI tool that would track the state of the IMU. So where's the gyroscope, where's the accelerometer, where's the magnetometer. And of course, once you try to play around with magnetism, you realize that if I just leave it on the desk and I walk past it, it will like go off the reservation. And we can also make sort of a 3D model of the computed pose afterwards. So I can sit and turn on the IMU, and the small 3D box will rotate accordingly. So that was quite fun, and it was also really useful in sort of trying to figure out where in the chain in this system things didn't work. And you can also see that there's something really funny going on with the timestamping in this particular trace that we captured. So the capabilities that we have in NetChan, or rather the logical channel abstract has seemed to be a fairly good abstraction. It works well, at least for the tests that we have done. It works well for periodic data. One caveat is that if you want to use the credit-based shaper, as I said, you reserve your bandwidth for either 4 or 8 kilohertz, meaning if your system like your IMU sends at 100 hertz, you need to subscribe for 80 times more bandwidth than you're actually using. So that means that you either need to look into multiplexing, or ideally you'll find a switch that supports one of the other shapers. Currently you have 2 options. I hope the asynchronous one is being supported soon. We'll see. You don't have to worry about all of the nitty-gritty details. There's a lot of effort gone into sort of hiding the SRP dance that you need to do to reserve bandwidth and everything. But as with all abstractions, you lose details. If you really want to know exactly what happened through the stack and to capture more timestamps, then maybe you want to use one of the vendor-specific libraries that gives you all the details, but also all the work you need to perform to send this. And I just want to emphasize again that this is not production-grade software. This is used to test around and see what TSN can do, to sort of give you something to mess around with and see if you can distribute your system using TSN. And if you can do that, then go find one of the vendor libraries to do it properly. So the outlook for this has been sort of a project for the last few years, and the funding has now run out. So I'm on the lookout for more funding. So I'm writing letters to the Research Council and everything. So hopefully I can pick up the pieces soon. I have some plans for using this in some energy grid applications. So look at distributing the fault controls of transformer stations, etc. And also there's some remaining work to be done. I have some analytical tools, some Python tools to look at the logs, etc. that are scattered all over my workstation that needs to go into the repository. And also make some wrappers for other languages. I have a really simple C++, which is basically a header file. It would be nice, especially for the debugging part, to have Python tools that you can to hook into. Those are nicely and dynamic, and it shouldn't affect the stream. So yeah, that was the end of the talk. Any questions, or is it, oh dear God, he has finished? Yeah. Oh, that's a very good question. Can you actually measure anything? So that, yeah, well, that's a really good question, actually. And if we go back, the basis of why we say we can measure anything, where are you? There. This is sort of the basis for why you can say that we woke up within 15 microseconds of each other, because we have measured the accuracy of the PTP clock. And we ran the measurements and sort of looked at the accuracy as we ran the experiments to see this is how much we adjusted the clock. Granted, this is done in software and reported by software. If you really want to do this accurately, you need to extract sort of a pulse per second or something from the network card, attach it to a scope and measure it. But this is sort of good enough for the test that we did. And the other one, looking at the, going to be a lot back and forth here now, sorry.
PCI Express one.
There's one. So you see you have a few outliers here, but most of them are centered around the center. So giving you an average of 28 nanosecond, it claimed to synchronize the system clock, but you had to sort of assume that is a 1 millisecond drift either way because of the outliers. But this is sort of as accurate time stamping as we can get on the systems that we had. Interestingly, if we did this, these systems run PCI Express 3. When I did the exact same measurements on my workstation that runs PCI Express 4, it's an order of a magnitude better. So 100 nanoseconds instead of a microsecond. So PCI Express 4 is way better at doing this. And apparently there are some more pieces in PCI Express 5 that you can instrument to prioritize traffic over the bus, but I haven't looked at that. But yeah, this is an interesting question. It's a difficult one, but yeah. Any other questions? Except for like philosophical one, what is time anyway? Yeah, and sort of the promised thing at the end. Yeah, how to start the daemons and also the QDisk setup. So basically we're using the MQ prior QDisk to prioritize traffic and sort of tie one priority to one of the hardware queues on the network card. And then you need this nice one at the top here, the MQ setup, where you tell it basically which priorities are going to be assigned to which hardware queue. So, yeah. Okay, well, then I'm done. Thank you.